So now it is my great pleasure to just give a brief introduction of Dr. Luke Burns. So Luke Burns is a physicist at Western Sydney University. He does research in the fields of galaxy formation and cosmological fine-tuning. Holding a PhD degree from the University of Cambridge, he utilizes numerical simulations to explore the evolution of matter in the cosmos. He is widely recognized for his work on the fine-tuning of the universe for life, investigating how minute variations in the fundamental constants of physics would render the universe uninhabitable. Dr. Luke Burns and Professor Grant Lewis are the authors of the Cosmic Revolutionaries Handbook, A Fortunate Universe, Life in a Finely Tuned Cosmos, with Cambridge University Press. So with this brief introduction, now I would like to invite Dr. Luke Burns. Sir, please, the stage is yours.
All right. Hello, everyone. Hopefully you can hear me. Hopefully I'm not too loud. Wonderful. Okay. So thank you very much for this invitation. I want to say a special well done to the organizers. I'm quite happy to be in the company that I'm in. There's some really excellent speakers who they've got lined up for you. So I'm very glad to be amongst them. So my topic for today is a fortunate universe, life in a finely tuned cosmos. It's been my experience that whenever I talk to any audience that I get up in front of, and literally 2 days ago, I was in front of some high school students in Australia, and the same thing happened. Whatever audience I'm in front of, whatever topic I want to talk about, someone will always ask about life out there in the universe. So the scientific picture we have of the world around us, we want to know where we fit in. And is there other life out there? Is one of the questions that comes up in connection with that. Now, that's not quite my topic here. My topic is definitely about life and how we fit into the universe, though. But let me start somewhere else. I have the great privilege of being an astrophysicist. So one of the wonderful things about being an astrophysicist is that the thing that we get to study, the universe, is an astoundingly beautiful place. Every new picture from this one from the James Webb Space Telescope, or from Hubble, or from any world-class observatory, or even a backyard telescope, is just mesmerizing, and it never really wears off. You never get bored of the universe, even when you're a professional astrophysicist. But what's wonderful about my job is that, as well as being able to appreciate the appearance of the universe, my job is to dig deeper underneath to understand why it is the way it is. So what you're seeing on the screen now is the center of a galaxy lit up in infrared radiation from dust, and you can see the sort of gravity pulling things together, the swirling motion of a galactic disk that's spinning around. You see holes in the gas of various sizes. The job of not just an astronomer to sort of take the data, but as an astrophysicist to try and understand what's going on here, is in the mold of the way that physics tries to explain things. So physics tries to explain things using three basic ingredients. First, the laws of nature. How does the stuff of the universe change and evolve? So, for example, gravity tells you, let's say Newton's law of gravity, for example, it tells you how things with mass accelerate each other, and so pull on each other. The laws of nature we know about, the sort of best laws we have, are all like this. They don't tell us how the universe is, they tell us how the universe changes. And that's quite important because it leads to the second factor there. If you want to know how the universe is, the laws alone won't tell you. You have to give them a starting point. You have to let them get their teeth into something. You have to, whether it's the initial conditions of the universe as a whole or just the system you're interested in, you have to give them a starting point from which to change. It's a bit like the difference between if I were teaching you the laws of chess and I told you how each piece can move, the bishop moves diagonally, for example. That alone isn't enough to set up a game of chess. I also have to tell you where to put each of the pieces at the start on the board. So physics explains by laws that act on initial conditions, but there's one more ingredient that sort of fits into the laws. What we find when we write down the laws of nature, the equations that describe the universe around us, we find that we need to put numbers into those equations. Now, usually the whole point of having an equation of a law of nature is that you get numbers out of the equations, because those are the predictions of the model that you have. To have to put numbers in is a very different thing. These are called the constants, sometimes the fundamental constants of nature. So for example, you're hopefully all familiar with electrons. The mass of the electron is, by some reckoning, one of the fundamental constants. So there is no equation that we have where you can sort of take that equation, solve the equation, and out of the equation comes the mass of the electron. We have to put that number into our equations. Now, we're perfectly capable of measuring that number. We know what it is. You can go and look it up. It's some very small number in any sort of normal human-sized units. But the point is, it's an assumption that we bring into the equations. Now, these, with one eye on the fact that we're going to ask the question about where we, as life forms, where we fit into all of this picture, it's important to know that these constants do play an extraordinarily important role in the way our universe works. So, for example, if you're familiar with the standard model of particle physics, you'll know that there is a bunch of fundamental particles, and you and me and this computer and everything we see around us are made fundamentally of three particles: up quarks, down quarks, and electrons. What our universe is capable of doing is taking those three basic building blocks, only three of them, and thanks to the forces that can hold them together, it can build up structure and complexity. So, for example, you probably know all this, but the protons and neutrons are made from quarks, two ups and a down, or two downs and an up. And then once you've got protons and neutrons, they will stick to each other and make the nuclei of atoms. And the electrons, thanks to electromagnetism, will go around the outside. How many protons you put in the nucleus tells you which element of the periodic table you are. So carbon has 6, for example, and there are 92 naturally occurring elements. But that they don't just sit there on their own. If you put two hydrogen nuclei and an oxygen nucleus close to each other, the electrons will orbit in a complicated way around that whole sort of Mickey Mouse shape, holding together all of the pieces, and that's a chemical bond. Our universe is very good at this. This is DNA. If you put these particular elements, hydrogen, oxygen, nitrogen, carbon, and phosphorus, in that particular order, you can literally write code. You can put the code for how you make a human being. Now, at this point, we're moving beyond physics and we're well outside of my expertise, but I'm told that the code will tell you how to make proteins. Those proteins you can put together to make cells, and if you put enough cells together, you can make small people, so I'm told. So if you go right back to the start of this story, there's the electron again, there's the up quark, there's the down quark. Their masses are right there at the sort of foundation of the building blocks of everything that we are made of. The reason this is particularly important is because if you started changing those numbers, you wouldn't just make a scale model of the universe. You wouldn't just make everything a little bit heavier. And there's an interesting reason for that. So the question we're going to ask now is, well, given that we don't know why these numbers are what they are, these masses of these fundamental particles, and a bunch of other numbers that describe the forces, we're going to ask, what if? What if the constants of nature had been different? Now, in total, there's about 31 of these constants that we know about that appear in the fundamental equations of physics as we know them today. So we can get busy trying to change them and seeing what's going to happen. So we've spent time talking about the electron, the up quark, and the down quark, so let's stick with those for a while. Here's a three-dimensional space. Now, if I ask you to pick three numbers to be the mass of the up quark, the mass of the down quark, and the mass of the electron, that's equivalent to picking a point in a three-dimensional space, right? Pick three numbers, or equivalently, think about this block in front of you and just pick a point in the block, and that will choose those numbers. Now, there are various reasons why we sort of cut off sections of the block. Up the top, you get very massive single particles, and up at the Planck mass, we would need a quantum theory of gravity to really know what's going on up there. So we'll just say, well, we don't know what's happening up there. Why don't we just um, cut things off at the top and at the back and at the sides, so we don't wander off into areas where we don't really know what's happening. There's another reason why it's cut off at the bottom, various sort of technical reasons in the standard model, but between those two limits, there are, as you can see, 60 orders of magnitude for you to choose from, and you can see where our universe is in the block. The sides of this, I should say, this is a logarithmic scale, so we're going up in factors of 10 on the side for up to 60 orders of magnitude. So, what if we changed those numbers is equivalent to what else is happening in other parts of the block? If I go wandering off to the left or the right or the front to the back, what would happen in those universes? Now, that's a question we can sensibly ask because it just is theoretical physics. What would happen in a universe with laws A, B, C, and D? That's literally my job. Like, what are the consequences of this law or that law or these laws? Now, usually we ask that question with one eye on finding the laws of our universe, but in this case, we're saying what else could have happened. So, let me give you an example. There's your block again, but I've carved off two sections around the sort of backside of the block. The reason you might want to avoid those is, whoa, my apologies. Something's happened there. Hack. What did I just do? Hang on, my apologies. Oh, keynote. Okay. Tried clicking something. We're back. Okay. Everyone stop panicking. So, it's very strange. Why can't I see the... All right, we're back. Never mind. Um, okay, so here's your no, back a slide. No, back a slide. Sorry. Enjoy this. Enjoy this atom for a short amount of time before I go back a slide and then we play the whole thing again. My apologies. Okay, back. There we go. Remember what we're doing. This is like your menu of like what sort of universe would you like? And so those universes around the back of this particular block, I'm saying you should probably avoid those for the following reason. In most of those universes, the thing that you make out of up quarks and down quarks, which in our universe, protons and neutrons, but in some of those universes, it's actually something different. It's either three ups or three downs. The real problem is they don't stick to each other, right? And so let's see this wonderful animation again. This is where most of the special effects budget went. Uh, so here's a simple atom in our universe, deuterium, if you're interested. Proton stuck to neutron, electron going around the outside. It turns out with a reasonably minor change of the fundamental constants, right? Because there's all sorts of things being held together here. If you change those masses, you can very easily make a universe in which protons simply don't stick to neutrons. Or to put it a bit more precisely, the system where a proton is attached to a neutron has enough energy to unbind itself. It's unstable. Actually, with slightly different changes, you can make it so the electron doesn't go around the atom, it spirals into the nucleus and turns the proton into a neutron. These universes are very different from ours. Here's the reason. Here's the periodic table again. Here's the astronomer's version of the periodic table. It's got a nice little symbol on all of these elements according to where this element is produced in the universe. But if you've changed the fundamental constants in your universe, if you chose from one of those bits of the block that I carved off, what you've got is protons that don't stick to neutrons, and protons don't stick to protons either. And so your entire periodic table looks like this. It's one element. You can't make anything else. Anything else just falls apart. So in this universe, the only element is hydrogen. The only molecule is the hydrogen molecule, H2, and that is the end of the chemistry lesson because that's really all you can do in those universes. Once we start considering criteria like this, and they're very broad criteria, like will anything be stable? You know, can I put two things together and have them stick to each other? Once I start thinking through those criteria on very general sort of energetic grounds, usually, like this has enough energy to fall apart and this doesn't, what you find is that what remains of the block is this thin slice here, um, in which, in that gray area in the block, you get 92 naturally occurring elements capable of doing all the wondrous things of chemistry that we see around us. You can, for example, find online databases where every known chemical compound is there in the database. There are currently about 120 million of them. But if you're outside that little grey region there, that number drops from 120 million to one or two, which is a heck of a change. It's quite a different sort of universe. So I mentioned how these calculations are done. One of the things that's relevant here is that these basic particles are also the building blocks, the fuel, I suppose, of stars. So let me give an insight into how this particular field uh, investigates the sort of conclusions I'm talking about. So, for example, here's a famous paper in 1989 by one of my fellow speakers here, Mario Livio, who may have spoken already or may be coming up, I'm not sure, but co-authored this paper in 1989. And it relates to a process by which stars in our universe make carbon. Now, we are made of carbon, but that's not the only reason to focus on carbon as being an important element in the universe. There's this thing supposedly called carbon chauvinism, where we just assume that because we're made of carbon, it's really important. Not true at all. Carbon is extremely versatile. And remember, we have all the elements in the periodic table. We can do the experiment to see which is most versatile. For example, if you go across the sort of first, I guess the second row of the periodic table, and you say, how many different compounds could I make using that element, say boron, and hydrogen? So I'll give you, if you think about going across the periodic table, I'll give you lithium and hydrogen, I'll give you beryllium and hydrogen, boron and hydrogen, carbon and hydrogen, nitrogen, and oxygen and hydrogen, right? And how many different compounds can you make? And for most of them, that number is 10 to 20. For nitrogen, it's about 70. And for carbon, it's about 30,000. Right, so carbon, just by a mile compared to everything else on the periodic table, is just phenomenally versatile. So it's rather important then, if you want a universe capable of doing interesting things, that your stars are able to make carbon, and ours make it via this process. You smash two helium nuclei together, they make a short-lived beryllium nucleus, but thanks to something called the carbon resonance, it hangs around just long enough for another helium to come in and make carbon 12. How would this process change if I change the fundamental constants of nature? That's actually quite an involved calculation, and thankfully for me as an astrophysicist, some nuclear physicists and particle physicists got busy and did it. So here is a series of papers. Um, the Modern Theory of Nuclear Forces, a review of modern physics by these three particular experts, whose name will be coming up soon. They, having reviewed and being experts in the modern theory of nuclear forces, then publish a lattice effective field theory calculation where they build up a very good, very modern, very flexible and versatile model for the nuclei with that many protons and neutrons in them. So carbon's the last one there. Then they calculate the this particular resonance, this way that a carbon nucleus can vibrate which allows for the reaction to take place a lot faster than it otherwise would have. They look in more detail at this. They look in even more detail and consider the effect of um, the light quark masses on Big Bang nucleosynthesis. And finally, the viability of carbon-based life as a function of the light quark mass. Now, there's a lot of work being done there. And behind the scenes, the method here involves these are some slides that I've borrowed from Meissner, one of the authors there. It involves supercomputers doing an awful lot of work. But here's the summary of that. This again is from Meissner. The End of the World Plot is the rather entertaining title he's given it. But what you can see in the sort of yellowish, orangey, I suppose, squares, the light quark mass is tuned to 2 to 3% of its value in our universe, and electromagnetism is tuned to 2.5%. If you changed the masses of the light quarks by more than that, this process that makes carbon in our universe wouldn't work. It wouldn't make carbon, or it would turn too much carbon into oxygen. But there's some sort of caveats here. You've got to be careful about how you do this kind of work. Because as Fred Adams pointed out, if you change the light quark masses and the some other constants in just the right way, you might end up finding another way of making carbon that's not this resonance. For example, if beryllium 8 were stable, you could just do it via the intermediate state. You wouldn't need this resonance at all. But it's still very interesting that we seem to be on a very sort of narrow strip of interesting universes. There's a look at what happens when you change the constants that inform the small things in the universe. We can also go to the large scale and look at the way that large scale structure forms in our universe. So here's a simulation. Now, this probably isn't doing particularly well over Zoom, but if you look around, I think this simulation is on YouTube and you should really go and find it. But this is what a supercomputer simulation of how we think galaxies form, done by the Eagle collaboration. Um, and what you see here within an expanding universe is that, well, the short story is that gravity pulling things in is making the dense bits of the universe even denser. So you can see here the knots, right? The sort of intersection here of all these points are getting denser and denser, more and more stars and are forming in galaxies there, and really clusters of galaxies on this sort of scale. The overall pattern you see here is, for obvious reasons, called the cosmic web. So you have the bits where the galaxies are, these sort of voids over to, where you see the holes, and then the filaments running between them, which haven't quite decided which way they want to run. So this is the want to fall. So this is the way we think structure forms in our universe. This simulation, by the way, takes a supercomputer a month and a half to do, and so this really does, in terms of a video for a minute, there's an awful lot of very clever people's careers are spent in doing these sorts of simulations and then comparing them to observations and then trying to improve them. So the remarkable codes here. However, if we rewind back to the start, in our minds at least, and start thinking about changing some cosmological parameters, changing some of the numbers that describe the initial conditions of the universe that you see playing out here, it's again quite easy to make a universe which is a bit boring. For example, if you weaken the force of gravity, then overdensities in the universe just don't collapse. You don't have a universe which brings smaller lumps together into bigger lumps, or if it does it far too slowly. It's important to remember how much work our universe has to do on this particular um, scale. The average density of the universe, right? If you just sort of picked up a random bit of the universe and measured its density, how many kilograms per cubic meter. If you took that number and compared it to the density of, say, air in this room, What you would find is that the average density of our universe is much, much lower, about a billion times lower. So we really need that structure to form so that we get things like stars. But you also need to get the constants right in order to have stars um, be stable in our universe. So, for example, here's a video of the sort of structure of the sun. What's happening here, and actually astrophysical models of stars are remarkably effective and successful. The short story is that in stars, a gravity pulling in is matched by heat or thermal pressure pushing outwards. What's important in our universe is that it's a stable equilibrium. So gravity pulling in, heat pushing out. If gravity pulls a bit harder and makes the star contract a bit, it will heat up, and so the heat will push back even harder, and the star will return to where it is. If the heat pushes back too far and the star expands, it will cool off, and gravity will pull it back in. So the there's not just an equilibrium, a balance between the forces, but if the star tries to step away from that balance, it will be pushed back into balance in our universe. However, if you take those very successful models of stars and you start to say, well, what if I made gravity stronger? What's interesting is that it's very easy to make stars that don't return to order, that overreact and blow themselves apart. Anything big enough to burn is simply big enough to throw off some of its matter entirely and to stop being a star. If your gravity is really strong, or equivalently, if you start your universe off far too dense, what you will have is a universe full of black holes. And that's no good either. So much of the energy we see around us, the energy that ignited the sun, for example, in the first place, came from the collapse of matter under gravity. So if you start a universe off with black holes, you've sort of used that form of energy up already, and the universe is a much more boring place because black holes, well, they will collide with each other, but they won't do much else apart from just eating things around them. There's other ways to get the beginning of the universe wrong. At one point in the history of cosmology, up to about 30 years ago now, these we thought were the three options. The universe had a start. You see those three start points down the bottom. It then expands. You see all those three expand as we go upwards. Uh, but was it the case on the left that the universe stopped expanding and came back and crunched? Or the one in the middle you can see there that it just sort of keeps decelerating forever but never quite turns around? Or the one on the right that actually it expands too fast for gravity to have much of an effect and just sort of coasts off into the distance? Those were the three options for what we thought the universe was doing until about 30 years ago, where the universe threw us a surprise that actually it's a fourth option, which was always available in the equations. We just didn't think it was very likely that the universe is in fact accelerating. A distant galaxy out there in the universe is not only moving away from us, it's moving away faster today than it was yesterday. Why is that happening? Well, as we looked around for an explanation, there seemed to be a good cause of this behavior at hand. Ordinary matter won't do this, but if empty space is filled of vibrating and oscillating and doing quantum strange things, fields, uh, even though there might be no particles there, which in practice means if you put a particle detector there, it would not go off. But if the fields are still there oscillating around, then some amount of mathematics later, let me just hand wave over all of that, we get a prediction that, oh, that energy in the form of these oscillations in empty space, that form of energy would make the universe accelerate in its expansion. However, this theory of dark energy, this particular theory of dark energy, mismatches our observations by an enormous amount, by 10 to the power of 120. In other words, if we just sort of thought, how much energy would there typically be over here, oscillating away in the universe? Well, an awful lot more than we actually see. So most universes, the sort of typical universe in which this is true, and we have very good reasons from particle physics to think that there are these oscillating fields in empty space. Uh, if you had these energies being as large as they seem to typically be, but negative, what would you get is a big bang that ends very quickly in a big crunch in a tiny, tiny fraction of a second. But on the other hand, if they're the size we think they are, but not negative, which leads to a crunch, but positive, what you get is a big bang that very quickly just accelerates off into the distance, and you get an empty universe. In that sort of universe, the sort of scenario where one proton bounces off another proton would be extraordinarily rare. So that's a properly, well, a beautifully simple universe if you're an astrophysicist. You don't have to worry about stars, planets, gas clouds, galaxies. You don't have to worry about any of that sort of stuff. None of that happens. At the most, a proton will bounce off a proton. As long as you understand that process, and the electron bounce off electron, proton maybe collides with an electron maybe once in a trillion years. Once you've got those processes, that's all you need to worry about. The universe is beautifully simple. There is no one there, unfortunately, to see that. Our work, my co-author, Geraint Lewis, and a bunch of our colleagues, including those from the Eagle collaboration, part of our work is actually to use that code to flesh out this, what I've shown you with simple animations, actually in detail via simulations. So nothing's happening on this slide yet. Relax. But when I hit play, on the left-hand side is going to be a universe which is approximately our universe. And the one in the middle is, what if those quantum oscillations in empty space were 10 times larger? Or what if they on the right were 100 times larger? Remembering that a typical universe, they might be 10 to the 120 times larger. So what you could imagine is, here's our universe 10 times larger, 100 times larger. You could imagine off to the right of the screen there, another, 118 panels. So using that same code that was used to calculate with a reasonable degree of success the way structure forms in our universe, let me hit play now. They all start with roughly the same initial conditions, but on the left, while structure forms and wonderful things happen like galaxies and stars and planets, you can already see over on the right what this increased acceleration does to the universe. Everything gets too far away from everything else. Structure doesn't form just because that process by which gravity brings things in gets shut off quite quickly. And that's only for 2 orders of magnitude more than in our universe. There's another 118 to go. This particular problem, right, it's called the cosmological constant problem. Now, there's a couple of different terms here: cosmological constant, vacuum energy, dark energy. For our purposes here, we can treat those sort of the same. But let me just go into a little bit of detail about why it's such a problem. First of all, it's actually a bunch of problems. It's several problems at once. So here is Einstein's equation of general relativity. This is what describes the expansion of the universe. The problem is, right, that one quantum field will add a very large term over on the right where the energy density is, the stress energy tensor. Every other field will also add another number on the right-hand side. When I say add, it could add or subtract. It could be positive or negative. So what's happening on the right-hand side, as a sort of roughly what's going on here, is, a whole bunch of independent processes, so far as we know, all the different fields of the universe, throw a number over on this right-hand side, which then gets added to, actually, there's one on the left as well, which we don't know why that would be what it is, but a bunch of numbers end up over here. All of them are enormously larger than what's observed, yet all somehow magically cancel out, and the universe doesn't blow itself to bits, and here we are. Each of those contributions is a cosmological constant problem, so it's really several problems. Secondly, general relativity won't help you solve this problem because general relativity doesn't tell you what the universe is made of. It tells you how the evolution, especially the gravitational sort of dynamics of the universe, depend on its energy contents. It won't tell you what's in the universe. And so it won't tell you, oh, there's definitely no, extremely large quantum fields in there. Particle physics probably won't help because particle physics is blind to the absolute scale of these energies. Only gravity knows about the absolute scale. Particle physics only depends on the relative scale. Fourthly, it isn't just a problem at the Planck scale, so quantum gravity won't necessarily help. We know enough physics and we've tested enough physics to know that this problem exists without having to know or even guess what's up at the quantum gravity regime at very high energies. Fifth, there are other forms of dark energy, other things that could make the expansion of the universe accelerate, but those don't erase the vacuum energy, and they could have exactly the same problem. Why are they so small relative to the value they could have had? Six, since 1998, we can't just say, oh, there is no accelerating expansion. That can't happen because we know it is happening in our universe. And on a related note, seven, if cosmic inflation happened, which I haven't really talked about, but it's a very rapid acceleration in the early universe. If that happened, then a life prohibiting acceleration is physically possible. So you can't rule it out with any sort of symmetry. Eight, there's a very clear connection to what I've called the anthropic limit to life. It's very clear that if you completely blow the universe apart and no proton ever touches another proton, then you're not going to get life. Right? I don't care what your definition of life is. A proton in empty space is not alive. And nine, this calculation we do to say what quantum, what might be out there in the quantum vacuum is known to be correct in some environments. It's called the Lamb shift. The method we use for that, you can't just throw out that method because that method works. So we really are painted into a corner here that there does seem to be an awful lot more space for universes that do life prohibiting things. So here's a summary. There's more cases that we discuss in the book, but of all possible values of the fundamental constants of nature, the subset that permits the existence of life seems very small. That's the sort of summary of what's going on here. Let me give you a brief overview of the way people have responded to this, and then we'll get to questions. My favorite response is this one. I'm not religious, but something weird is going on here. I find that very funny. Um, the instinct here goes a little bit like this, right? At some point, hopefully this video is doing well over all of the internet, but it's a hummingbird flapping in slow motion. There's something really remarkable about the stuff that's in our universe that we know around us, right? The protons, neutrons, electrons, quarks, and all that sort of stuff manages to pull itself into the form where it can do the thing you're seeing on screen. I've been using this illustration for a while, and I think the internet heard me because it started showing me ads for this, trying to sell this to me, and I'm slightly tempted to buy one. The reason why this fine tuning is it's unnerving because actually it's extremely familiar. We're very familiar with what's happening in fine tuning. It just seems completely out of place in physics. So why look at the thing on screen. Look at one of the say cogs, right? With the gears on the wheels. Why does it have exactly that many gears? Cogs on the edge of the gear. Why is it exactly that size? Well, because someone thought out ahead of time that it would go exactly in that place on exactly this contraption and do exactly the thing it was supposed to do. That's the sort of thing minds do, and it's so obvious and so common we don't really stop to think about it. But what's weird about fine tuning is it seems that our universe at its beginning had certain properties so that later on it would make stars, planets, galaxies, and life. Now, that's not the sort of explanation you get within science, right? The things are as they are because of what's there at the time, and then the laws just play out. It's very strange to see the universe seeming to plan ahead. So, what are the other options for explaining the way that our universe is? One of them is that we just need to do more physics. The laws as we know them have the fundamental constants as we know them, but new physics could come along tomorrow and show us that these constants, maybe they're actually dynamical quantities. They vary from place to place, but really the sort of grand hope here is that more physics will show us that these constants couldn't have been different, that we'll understand why they are exactly why they are, that we'll find that deeper equation that allows us to get the numbers out of the equation rather than having to put them in. That's a hope. At the moment, we don't know what physics will do tomorrow, so we don't really want to sort of prejudge that. There's a very interesting paper from Bernard Carr and Martin Rees from 1979, which makes the following comment just as the paper ends. It says, okay, maybe all, I'm paraphrasing, maybe some deeper mathematical symmetry will explain these numbers and explain the coincidences between these numbers, but it would still be a bit strange if something as abstract as mathematical symmetry explained why the universe is capable of producing life. It would be weird if the only mathematically possible universe was one in which hummingbirds exist, for example. Another option which is discussed is a simulated universe. I mean, I make universes in a computer. Maybe ours is made in a computer. Maybe we are the product of a simulation in the universe upstairs, so to speak. Now, what's interesting about that is um, if our universe, not, remove the thought that maybe there's a programmer in the upper universe or whatever that is, but if our universe is fundamentally digital rather than analog, if you want to put it that way, there might be ways that we could observe that. And that would be interesting. Nothing's turned up so far, but it's worth thinking about. Finally, maybe we won the cosmic lottery, the multiverse. Now, you've already had some talks about this, I think, but the idea is very simple in terms of fine tuning, right? There's maybe out there, there's lots of other universes. They all have different properties. And if we went looking into them, we'd find that for these fine tuning reasons, most of them don't have any structure inside them. Most of them, for example, get large or very large and negative cosmological constants and just blow themselves apart. But there's no one around in those universes going, oh man, what went wrong around here? All of the people who are asking the question of why they're in the universe they're in are in a universe that's right for life. And so there's the explanation. Now, on one level, that's for me as a physicist, that's something I want a detailed model about. I want to go and do predictions. That's why we did those simulations I just showed you to try and understand, try to test some of these models. I'm not sure whether it's going to answer that deeper question of why is there something interesting and rare going on around here? Because it seems like it might just push that question up a level, that a fine-tuned universe would just suggest a fine-tuned multiverse, and we still find ourselves face to face with a universe that's doing something interesting and rare. But that's the sort of where the debate is at the moment. Those are the live options. I'll leave you with the book if you want to dive into those anymore, and say thank you very much for your attention. I'm looking forward to your questions.
Thank you, Professor, for your wonderful talk. And also, thanks for highlighting very important empirical study of this fine tuning and also sharing some papers and simulations. So, thank you very much.
Hmm.
So, now we have got a few questions from our participants. So, we will have our first question by Rajesh. So, he's asking, how robust is the evidence for fine tuning? Could some of this fundamental constant be varied without eliminating the life? Do these constants drift with time?
There's a couple of questions there. First of all, a lot of effort has been put in to try to work out whether these constants drift with time, because that would tell you it's obviously not a constant, but that would be very, very interesting. Um, Again, a lot of effort's been put into that. At the moment, there's no evidence that they change in a significant way. One of the ways you do that is by looking at the sort of furthest thing that you can see, which is usually a quasar out there in the universe, and see whether the relationships between the electron levels that we see in the emission lines, whether that's changed. So um, the reason why that's very useful is because if one of the fundamental constants changes, that immediately tells you there's something wrong with the um, laws of nature we think we have at the moment, the standard model. They have to be wrong because they say that they're constant. And so you can go ahead and book your ticket to Stockholm because that's probably worth a Nobel Prize, but nothing's turned up. These constants, as I said, there's 31 of them. I should say a lot of them, probably most of them on balance, actually, because they relate to parts of the universe or pieces of the universe that don't affect life, they actually aren't particularly fine-tuned. For example, a bunch of the constants relate to the properties of neutrinos, and all life really needs from neutrinos is that they don't bother us too much, which there's neutrinos from the sun passing through your body right now. So a lot of the case studies I've presented, I think are very robust. As I said, we've done simulations, the work of Fred Adams, particularly on stars. We've written some papers on that stars as well. The sort of papers I shared about the way particle physicists are doing things. Um, um, Actually, you're not the next speaker. The one after is Frank Tipler. Frank Tipler and John Barrow in 1986 wrote the sort of classic book on this, The Anthropic Cosmological Principle. A lot of those arguments back then were very back of the envelope, very rough order of magnitude calculations. But by now the field, like we're trying to answer these questions with the sort of best simulations we have. So I think in terms of the physics we have, a lot of the cases, as long as you're up to date and a bit conservative with the way you present it, are very, very robust. But we don't know what physics is going to tell us tomorrow. So it might tell us something entirely new about a quantity that we thought was a constant. So, yeah.
Yes, thank you, Professor. So next question, please. So this is question by Professor Lewis from York University. So Professor is asking that in chess, pieces can be captured and removed from the board. As a result, the game eventually ends. In the universe, energy conservation precludes any change in the number of particles. The game of the universe doesn't appear to have any rule that will make it end, and from symmetry, we can't talk of an initial position either. How can we know that the universe had a beginning if our interpretation of redshift is still debated?
Ooh, very interesting. Um, so there's a couple of interesting questions there. Yeah, very interesting. First thing to sort of drop a bombshell here in conservation of energy from what's called Noether's theorem follows from time translation symmetry. And the expansion of the universe means that the universe is not time translation symmetric, so actually doesn't conserve energy. More than that, energy conservation does not preclude any change in the number of particles. Particles are not conserved. Energy, even in the smaller scale where energy conservation still applies, um, that it doesn't imply conservation of particles. So, for example, I mean, there's a light bulb right above me. It's producing photons at a phenomenal rate, but it's not. There's no conservation law there. Every time electron goes between two levels, out comes a photon, and then you can just keep making those. So you've got to be very careful if you want to talk about the way what the universe is going to do next, because it's quite you've got a lot of work to do to try and work that out. The game of the universe doesn't have a rule that will make it end. Um, we can't talk of an initial position either. That's where I think there can actually be an asymmetry. There can be different things according to the models, according to the best physics we have. There can be differences about each end of the universe, the beginning and the end. It could have a beginning in time. There was, a point where there was no second worth of time before that point, but still be sort of eternally infinite into the future. How can we know that? Well, what we need is a theory about how the universe evolves that we sort of trust to take us sort of extrapolating back that way. We have general relativity, but for various reasons, we think that quantum gravity might have to replace general relativity at some point. Although, in 2 talks' time, as I said, you're about to hear a talk from a guy who doesn't think that, Frank Tipler. He might mention that point. You could ask him about it. Um, one final point there. How can we know the universe had a beginning if our interpretation of redshift is still debated? No is a very strong word there, but I want to say that, the interpretation of redshift as due to the expansion of space is very, very well established, does an excellent job of explaining what we see around us. My book with Geraint Lewis, The Cosmic Revolutionaries Handbook, will present that case if you want to see that one.
Yeah, thank you, Professor. So fourth question, please. So this is question by Pradeep Kumar, Kendriya Vidyalaya Sangathan. Thank you so much for such an enlightening and profound lecture on the fundamental nature of our universe. If I may, I would like to ask, while your work brilliantly demonstrates that the physical constants are finely tuned to permit the existence of complex matter and life, do you believe that this tuning extends to the emergence of subjective awareness itself, or does the hard problem of consciousness requires a separate explanation that alone, no matter how finely tuned, might not be able to reach?
Yeah, so basically, does fine tuning shed any light on the hard problem of consciousness? I'd say no, it doesn't. Um, exactly what the universe needs to do in order to produce consciousness is just beyond me. I'm just an astrophysicist. I find the hard problem of consciousness to be, one of the things in life that you should really sit down and really have a very hard think about. Because especially for me as a physicist, I do these simulations, I write the code, I set it going and the unit and off it goes. I know what it means to say I have a sort of universe in the computer, and within that, it made a galaxy. There's some arrangement of things that I can say that's a galaxy. I don't know what it would mean for me to look inside the universe that I made in a computer and say, oh, it's conscious. It's having a first person experience. I just don't know what on earth I could possibly do looking at the universe I made to reach that conclusion. So, like I said, I don't offer any sort of conclusions about the hard problem of consciousness.
Yeah, thank you, sir. Yeah, it's really very hard. Yeah, thank you. So, next question, please. Yeah, this is question by Jagdishwar. He is asking, if the physical constants of our universe occupy a vanishingly small region of possible parameter space, as illustrated by the 60 orders of magnitude gap between the electron mass and the Planck mass, is the
Hmm.
fine-tuning problem scientifically meaningful without a well-defined probability measure over that space? And can such measure ever be empirically grounded?
Very good question. If you want to hear the voice of someone who's very skeptical about all of these, Sabine Hossenfelder is a name you can find. She wrote a paper in 2018 called, I think, Screams for Explanation. Anyway, it's basically saying no to the question you've asked. My response to that would be when in science we want to weigh two separate theories. We've got our observations of the solar system, for example, and here's Newton's theory and here's Einstein's theory. Um, we need a way of weighing those two up. So at the end, we can say something like, well, given the data I have, Newton's theory is more probable, or Einstein's theory is more probable than Newton's. In order for that to be a meaningful statement, you need an idea of probability which doesn't just come out of the observations, which comes out of sort of the theories themselves. I think that's what Bayesian probabilities do. So there's this approach to probabilities where you treat probabilities not as descriptions, sorry, statistical descriptions of data, or even the sort of stochastic probabilities of things in our universe, but as degrees of support between one idea and another idea. And so, how much does the data support Einstein? Well, it's not like we have 100 universes and in 99 of them Einstein's rules. So we need a different idea of probability. That's the approach I would take. I've defended that in a paper called A Reasonable Little Question, if you want to go and look up that particular paper.
So this is question by Bach by Bangalore University. Is asking, can you rule out interaction between different universes? If not, are there any signature of such interactions?
We can't rule it out. So the thing to do with that is if you have a model for what interactions would look like, and if there were signatures of that, you would sort of run that model. In practice, however, once you start the sort of models we have, and they're quite hand wavy, but the sort of models, Andre Linde probably talked about them, where inflation produces a multiverse. Because you're relying on a process which expands the universe so quickly, this accelerating, inflating um, expansion, the bits of the universe, the sort of individual universes in the multiverse end up so large that it's very unlikely that you're near the edge of one. So there would be edges between, here this universe has some property, and then just over there, there's, electrons are heavier or lighter or something like that. If you're going to have a working multiverse theory, there must be places like that. But in almost all multiverse models, the universe domains, the sort of individual universes, are so large that it's not a prediction of those models, or extremely unlikely on those models that we would be anywhere near the edge of the universe. So this is a real worry, because what it means is that your one hope of directly observing some prediction of the multiverse, that maybe there is a different electron mass over there, is almost got no hope according to the multiverse. You just won't directly see any other universes. So that sort of confirmation of your theory is almost certainly impossible.
Yeah, thank you, Professor. Next question, please. So this is question by Ritwik. Can you explain about Hoyle's state carbon resonance favoring the abundance of carbon in universe? What can be the explanation behind this?
So Hoyle, this is one of the first sort of most famous cases of fine tuning. If you just do a basic calculation of, if I had a star full of helium at a certain temperature and I just let it go, how quickly would it make carbon? And you do a basic calculation, and the answer is extremely slowly. Um, and so Hoyle thought, well, that can't be right, because there is carbon in our universe, so there must be something else going on here. There's a way to accelerate these reactions if there's what's called a resonance in the carbon. There's just a certain way that it can handle vibrations and sort of live for a bit longer, so to speak. The maths behind this is part of quantum mechanics. It's sort of hard to explain, but that's the short story. On the basis of this, Hoyle actually predicted that resonance. He said, well, if this resonance isn't there, stars won't produce carbon. And so he called his friend Willie Fowler, who was a nuclear physicist, and said, look, I can tell you where to find a resonance in the carbon nucleus. And he was right. And he absolutely should have won the Nobel Prize for that. And it's ridiculous that Hoyle never won it. So that's then Hoyle said, this, his quote later on was, it looks, I'm paraphrasing here, but it looks for all the world like a super intellect has monkeyed with physics, right? The properties of our universe were set up so that it would produce carbon. There's a little footnote there, as I mentioned during the talk, that there's other ways you could make carbon by, say, binding beryllium, but uh, whatever the case, it seems that there's this sort of there's lots of ways to make universes in which there's not much carbon around, and ours is one that is able to make plenty of carbon. So why is that? Is the question of why our universe is fundamentally the way it is. Maybe there's deeper physics. Maybe we got lucky because we're part of a multiverse, or maybe someone's thought it through beforehand before making the universe.
Yeah, thank you, Professor. So we will take a last question. This is question by Dr. Aniket Chowdhury. Given that the cosmological constant must be fine-tuned to 10 to the power 120 for galaxies to form, the strong force coupling must be fine-tuned for the Hoyle resonance to produce carbon, and the
Mhm.
electron mass must sit at precise point in a 60 orders of magnitude parameter space for stable chemistry. Are these independent fine-tunings are symptoms of single deeper constant whose mathematical structure we lack the conceptual vocabulary to even pose as an equation?
Right, a couple of things there. I mentioned my paper, a reasonable little question. Um, the 120 orders of magnitude, there's ways to soften that, just to do some technical stuff first. If you start varying other parameters, there's ways to have larger cosmological constants and still get life, as long as you can do some other things. But the short story is, you do have these interesting fine tunings, I should say. The electron mass one is probably actually about 17 orders of magnitude. The 60 orders of magnitude was just the possibility space. Um, are they independent? Well, what we're doing here when we do fine tuning is taking stock of where we are, right? Here we are. We have a really remarkably successful set of models that tell us about particle physics, tell us about the expansion of space, and they're very interesting and very useful. And now we ask the question, all right, well, is there anything sort of rare or interesting or special or remarkable at the way the universe is that we see around us? And the answer is, well, yeah, most of the other ways that we could sort of model a universe, it doesn't do the interesting stuff that ours does. Is there some ultimate constraint that's deeper and behind the scenes that might explain it all? Maybe. The weird thing about that would be, as I said, that paper by Bernard Carr and Martin Rees, it would be a little bit strange if, it would just be another deeper coincidence if mathematically beautiful symmetries and what a universe needs to do to make hummingbirds were the same criteria. That would be rather strange, don't you think? Although it's harder to sort of quantify, but there's still, even if there was a sort of deeper explanation in terms of symmetries, there'd still be something strange and unique and weird going on around here.
Yeah, thank you, Professor. So thank you, sir, for addressing these questions in quite detail.
Absolutely. Thanks for your questions, everyone.
Yeah,
Very
thank you, sir.
good.
So on behalf of Bhaktivedanta Institute, I would like to thank for sharing all your insights in the lecture, and I extend our sincere thanks for everything, sir. Thank you.
A pleasure. Thanks, everyone.